Now, in the last class we have discussed about one of the application areas for hydrocyclone in solid liquid separation. Now, there are two extreme cases even in that, in solid liquid separation, and those two extreme cases we give different, we use different terminologies. One we call it clarification, another one we call it dewatering. The clarification means separation of solid from liquid. That means, my target is to separate the solid from my liquid medium, mostly the liquid is water. So, then we call it the clarification. In another case, we call it dewatering, where the separation is aimed at more on the liquid than the solid. That is, I want to recycle back that water, I want to get rid of that water from my pulp. So, that is where we use it. Why we use these two terminologies? Because when we know that this is a clarifier or this is a clarification, this cyclone is used for clarification, we know that what is the job it has to do. When we know it is dewatering, we know what is the job it has to do. That is why we give the two different terminologies. In both the cases, the extent of separation depends on the feed size distribution, that what is the size distribution of your particles you have. The feed slurry characteristics, that means whether you have got a very dilute suspension or you have got a thickened one. That means, what is the relative percentage of solid into your slurry. If you have a dilute, you do not have rheological problem, but if you have relatively higher percentage of solids, you have to take into consideration the rheological characteristics of that slurry. What are the design and operating variables of cyclone? So, the design, although it is cylindro-conical, but as I said that what should be the angle of this conical part, what should be the cylindrical diameter, what should be the length of the cylindrical portion, what should be the inlet diameter, what type of inlet diameter, what should be the underflow orifice, that is the spigot diameter, what should be the overflow orifice, that is your vortex finder diameter, what should be the material of construction, all these come into picture. We will discuss briefly about all these design and operating variables at later time. So, for these cases, a cyclone which is long in relation to its diameter is preferred. That means, when the conical part is much longer than the cylindrical part, that is what is being used. What does it mean? So, that means, when the included angle, that is the cone angle, is smaller. So, when the cone angle is smaller, what will happen? Now, you will be generating much more centrifugal force in that area. So, your mv square by r, because your r is smaller. So, you can generate more of in situ, you can intensify the centrifugal force in situ, and when the centrifugal force is more, so you can even have the solid particle separation to be possible at a relatively finer sizes. And because of that also what will happen, the more pressure drop will be created. So, at the velocity of my air core, you can increase it, so that more of my water can be transported through the overflow. So, that I can have your separation between your solid and liquid in a much faster rate and much more accurately. The cyclone in combination with other methods of separation is generally used as a thickener. That means, when we are using it as a thickener, that is for solid liquid separation, whether it is clarification or whether it is dewatering, then we try to separate most of the solids or majority of the water from that, but as I said that the cyclone separation is never perfect, it is far from perfect. So, we try to combine with other mechanism also, like maybe the cyclone product, that is your, say suppose we are using it for a your dewatering purposes. So, that solid liquid, that is your thick and your slurry, what you are getting it into the underflow, many times we try to send it to a filtration unit, that is for your further dewatering purposes, or maybe we can send it to a thickener, that is where we add polymers and then we try to flocculate them and we try to have much more separation between the solid and liquid. Now, solid from solid, that is a very important application for hydrocyclones, as I had explained you. That is why I said that the hydrocyclone is probably the heart of any mineral processing plant, and that is for solid solid separation, that is your separation based on sizes, that is where it is used as a linkage between your combination circuit and your processing circuit, that is where it is being used as a classifier, that is your solid solid separation based on their differences in the sizes. So, this solid from solid separation could be based on the differences between size, that is when it is based on size we call them as a classifier. When we try to separate based on the density differences, we call them as a your density separator, like your dense medium cyclone, and many times you can use it also for separation based on shape, but it is not that preferred equipment, or it is not that frequently used in mineral processing industry for separation based on shapes, whereas in other industries like food processing industry, they are using cyclones for separation based on shapes. Separation based on size is termed as classification, that is your centrifugal classification. Low efficiency of particles below the cut point and high efficiency above it are the desired objectives. That is what I want in simpler terms, that is we want that your hydrocyclone should give me a size based separation what a screen would have given me, or what an ideal size separation device would have given me. That is, I want to have a separation at 40 micrometer irrespective of the particle densities. So, I should get that type of separation into a hydrocyclone, but that is what is the desired one, but we hardly get it. Removal of fines from coarse particle is termed as desliming. We have discussed it many times. We have seen also that even the your mechanical classifiers, or maybe the spiral classifiers, like your spiral classifiers, we can use it as a desliming unit, and many times when the desliming has to be done at a relatively finer sizes, we use it the cyclone, and when we use it for desliming purposes, we call it desliming cyclone, and is of wide interest in the treatment of mined products, because mostly the mined products we have got clays. So, we want to first get rid of these clays at the very beginning, so that it does not interfere into my other separation processes, because these clays are very fine particles, they will increase the viscosity of my fluid, and then I will have problems in the material flow characteristics into a fluid medium. Removal of coarse particles from fines is termed as degrading. Like many times we use it, the cyclone, that we have got certain amount of coarse particles coming from my upstream processes, or maybe many mined like your quarry products. Many times I want to have a size product, say suppose from 100 micrometer to your 50 micrometer, and you have got a few particles which are even coarser than your 500 micrometers. So, there also we can use this cyclone, and when it is used for that we call it degrading purposes. So, removal of oversized foreign matter from many chemical products is an example. So, in many cases that we want to remove this your relatively coarser particles, and where the volumetric concentration of these relatively coarser particles is much lesser and we do not want them, and when we use cyclone for that we call them degrading. So, sometimes we want to remove the very fine ultra fine particles, then we call it desliming cyclone. When you use them for relatively coarser particle removal, we call them degrading cyclone. So, the design of the cyclone, the dimensions of the cyclone and the operating conditions of cyclone will differ based on the purposes for which it is being used. Then liquid from liquid separation, example I have already given it, that is separation of oil and water. That is, if you want to separate oil and water, you can use it, but limitations is that not possible to obtain complete separation in one stage and difficult to identify an optimum flow rate for maximum separation efficiency, as due to the shearing action emulsification of the two phases may occur. So, that is the your trouble. So, what should be the optimum your say your shearing action you can impose on this mixture. Anyway, that is not the part of our subject. So, mineral processing people normally does not have to deal with this liquid separation. Then gas from liquid, there is also another application. The use of a cyclone for this purpose is perfectly feasible. However, it requires departure from conventional cyclone design due to the necessity for non-axial removal of the liquid or destruction of the air core at the point of an axial exit, so as to avoid re-entrainment of gas with discharging liquid. Do not worry about this, I just wanted to tell you that even the hydrocyclones can be used for gas from liquid, but we normally mineral processing engineers are not interested to know much more on this subject, that is your liquid separation and gas from liquid, but I wanted to give you this information that if you are interested in this cyclone separator, you may look at the literature in many other industries, like mostly the chemical industries, they are being used, chemical and petroleum industries, they are being used extensively for liquid separation and gas liquid separations. Now, how do we evaluate the performance of a hydrocyclone? Hope you all remember that when we had discussed about the performance evaluation of industrial screens, that is a gentleman called Trump, what he proposed that do not look at that, do not evaluate the performance based on what you have got. You look at the different sizes of the particles, how much difficulty the individual particle classes they have faced in getting separated from the mixture. And based on that concept, I have already discussed and I have already shown you through a numerical example, that is how you have to calculate the difficulty in terms of partition coefficient. If you do not remember, I would request you to go through my previous notes or to previous lectures on industrial screens performance evaluation, you will get to know that. And there we have plotted the partition coefficient versus your particle size. So, here also we do the same thing, because its purpose when we are using it for size separation device. So, we have to look at the each particle class how much of difficulty they have faced. So, in that case what do we do? That is your feed appearing in underflow percentage. That means, what percentage of a particular size class they were in this feed, and out of that how much we have got it in underflow. So, that means, say suppose in underflow for a certain fraction from 100 to 90 micron particle, I have recovered 90% of the available material of that feed size, of that size particle available in the feed. So, that is the 90%, and that 90 we plot against the size, that is your 100 to 90, we take a mean size of that and we plot it 95 micrometer. So, like that when we plot it based on underflow, you can plot it also based on overflow, there is nothing wrong in that, but conventionally the mineral processing people they plot based on the underflow, because the underflow is easier to collect in most of the cases in the plant, and the overflow they are basically directly sent to a downstream processes, and the overflow. So, probably because of that reason that you collect underflow, and the underflow you have got lesser water. So, your time of filtration is less, your time requirement for dewatering is less in a laboratory, and you can do the size analysis very easily, and relatively coarser particle the size analysis is much more accurate than the much more finer particles. So, here what you do? You do this your recovery terms or the partition coefficient in terms of how much of a particular size was available in the feed, and how much of that you have recovered into the underflow as a function of your size. Then you get a curve like this, what you had observed in case of industrial screening also. So, that is called a real curve, that is called a partition curve. So, the commonest method of representing cyclone efficiency is by a partition curve. So, that is what a partition curve, and again if you remember that what we did, that what is the D50 size here. So, D50 size is close to 19 micrometer here based on this size. So, what it is saying that if we have an imaginary size separation at 19 micrometer, the entire your particle sizes would have been equally distributed into the oversize and undersize fraction at that size. So, now, so that is the D50 size 19 micrometer. Now, if I have an ideal separation at 19 micrometer, this curve shape would have been converted into a shape like this, that is I would have recovered all the particles in my underflow at 100% your recovery. I would have recovered 100% of all the particles coarser than 19 micrometer into the cyclone underflow, and all the particles finer than 19 micrometer I would have recovered them 100% into the overflow, because when the underflow is showing 0%, that means they have reported to the overflow. So, there is a deviation from this. So, again based on that concept, that is your D75, that is what is the D75 size here and what is the D25, we have already explained that this portion becomes the it will give you mostly the straight line, and because of that your concept of slope. So, this has come, that is the imperfection is the same formula we had used for screen efficiency calculation. So, that is D75 minus D25 divided by 2 D50. So, that is called the imperfection. So, what do we do? We try to calculate it, and for a perfect separation this imperfection value. So, the D75 would have been 100, D25 would have been 100, and I should have got it your say imperfection would have been 0 for an ideal separation. If you look at closely this curve, there is another interesting feature, that in most of the cases it does not pass through the your origin, that is at your 0%. It is somewhere it is going towards the your some percentage is remaining here. And the mineral processing researchers, they were trying to understand that why this carb is not passing through the at a point of your origin, that is your 0 point, because you should have an infinite size particle class which should not have reported, which should have 0% recovery into the underflow, but we could not do it because probably that we could not measure up to that size. That could be one reason, but that has prompted many mineral processing researchers to propose something, that is, how do I force this carb to pass through the origin. And for that many mathematical models have been developed, and instead of using a D50, they have proposed to use a corrected D50 term is taken from the corrected classification curve. I will discuss it, what is that. But for that there is an assumption. What is that assumption? So, assumption is that the solids of all sizes, are entrained in the coarse product liquid, that is, whatever the liquid is coming, that is your water is being reported through the underflow, in that particles of all sizes at a certain amount they are entrained into that, and the mechanism they have said that is by short circuiting, that is, once they are entering some part of the feed as it is, they are bypassing the by classification chamber, that is, thereby some means they are reporting through the underflow along with the water what is passing through the underflow. That means, they are not being classified, and this amount, the amount of this material is directly proportional to the feed water reporting to the underflow. So, that means, if I have 25% of my feed water reporting to the underflow, then the assumption is that 25% of my feed material will report to the through the underflow, which is not classified at all. That means, which has not been subjected to for size separation. So, what is the meaning of this? Now, suppose the feed contains 16 tons per hour of material of a certain size, of a size distribution, and you have a mean size, and 12 tons per hour report to the underflow. That means, you have a feed rate at 16 tons per hour, and out of that 12 tons per hour of that size report to the underflow. I am talking about a particular size fraction. Then the percentage of this size reporting to the underflow based on this conventional analysis, that you have got you are feeding it at a size, say suppose x, into that feed size distribution at a rate of 16 tons per hour. Out of that 12 tons per hour you are recovering that size into the underflow stream. So, what is this percentage underflow or percentage feed material reporting to the underflow? That is your 12 by 16 into 100, that will give you 75%. That is how the original curve is plotted. Now, what is this group of researchers they have proposed based on that? That is, if say 25% of the feed water reports to the underflow, then 25% of the feed material will short circuit with it. That means, they will not be subjected to classification, they will just 25% of the feed material. So, when the 25% of the feed material is coming, that means, the 25% of that particular size material will also come to the underflow due to short circuiting. So, 25% of 16 ton means it is 4 tons per hour. Of the size fraction will report to the underflow due to short circuit. So, only 8 tons per hour, that is 12 minus 4, will report to the underflow due to classification. So, that means, whatever 12 tons per hour of that particular size fraction you are getting through the underflow, out of that 4 tons per hour you are getting it because of short circuiting, because 25% of feed water has reported through the underflow. So, what is this corrected recovery now? So, the corrected recovery is 12 minus 4 divided by 16 minus 4, that is, this is 8 and this will become 12. So, this is 2 by 3. So, it is around 66.6%, or if we round up this becomes 67%. So, now based on this concept, if I calculate the corrected recovery of each particle sizes and then I replot it as a function of size, then we get a corrected classification curve and which should pass through the origin, and that is the corrected classification curve. So, this is my uncorrected one, that is what we have calculated based on simple mass balance, that is how much I had in my feed and how much of that particular size class as reported to the underflow. Based on that we have calculated. Now, when we have a corrected one, so now we have to take the corrected D50. So, previous example the D50 was 19 micrometer. Now, the corrected D50 denoted as D50C will become like your 22 micrometer or 23 micrometer. So, this is the difference between your corrected classification curve and uncorrected classification curve. Now, what is the advantage of doing this according to the scientists who proposed it? Now, this Professor Lynch of University of Queensland, he named it as reduced efficiency curve. He plotted another curve that is called a reduced efficiency curve, where he had plotted the d by d50c. D by d50c means that what is that size you want to know. Suppose I have got a size distribution. So, you have got a D50C of 22 micrometer. Now, the size what you are trying to plot in the x axis, say suppose that is 10 micrometer. So, that is 10 by 22. So, that is d by D50C. You are plotting it in the x axis and the feed to underflow, that is how much of that you have recovered into the underflow of that particular size based on the corrected your efficiency curve concept. So, what is happening when you plot it like this? So, Professor Lynch suggests that this curve can be used to derive the actual performance of a cyclone, as it is independent of diameter, outlet dimensions or operating conditions. What he has suggested that this reduced efficiency curve is independent of the operating and design parameters. However, this is my personal opinion that it may not be always true, because my reasoning is that your D50C, that is your corrected D50, depends on the operating and design variables and everything. So, but that is a debatable thing, and this is what is already documented in many literature. So, I just raised this question and I said that may not be always true. I leave it to you to have a debate on this topic, and you can try at your operation and see that whether it is always true. I may be wrong also. So, now based on this reduced efficiency curve, many models have been developed, and those models are basically frequently used in the industrial scale cyclone operation for their selections, for their your design and process parameter optimization. Anyway, we will carry on this topic in the next lecture. Till then, thank you very much. Thank you.